I'm also happy to be here virtually with you to share some thoughts about information and disturbance. So as you see from the subtitle, the scenario for this talk would be operational probabilistic theories, which are theories that generalize a bit what can be done in quantum and classical theory. And I give you first an outline of the things I'm going to say. I will start with a very sketchy, brief introduction, starting from the early days of quantum mechanics, so from Heisenberg thought experiment with gamma ray microscope, and then move immediately to present times with quantum information versions of the problem of information and disturbance for quantum systems. And then I will introduce operational probabilistic theories and try to set a larger scenario, a larger playground to formulate the problem of understanding the trade-off between information and disturbance, information that can be gathered in a measurement and disturbance that the measurement makes on the system. Of course, this would need to this would require a thorough definition of what is disturbance in this generalized scenario of theories, and then information extraction. And then we will formulate the notion of theories that have this feature, which we call no information without disturbance, so generalizing the features of quantum theory. And then I will show you a very nice necessary and sufficient condition for this to hold, for the information without disturbance to hold. And finally, we'll conclude with some remarks. So this is not really the kind of talk on strictly speaking on contextuality, but I think that among my research, this is one of the topics which is closest to the topic of the conference. And I would say that the fact that in quantum theory you have no information without disturbance is, in the end of the day, one of the roots of contextuality. So everything starts with the thought experiment of Heisenberg's, the gamma ray experiment, which was in his ideas should have been a way of making more intuitive is uncertainty principle, but actually the experiment touched some slightly different problems, somehow different from the statistical indeterminacy, which is the actual content of the indeterminacy. So as I was saying, the idea of Heisenberg was to give an intuitive explanation of his uncertainty principle, which actually talks about statistical indeterminacy of conjugate variables, but actually touched a slightly different problem, which is the interplay between the amount of information that we can gather about some observable in quantum theory and the amount of disturbance that we do on the state. So in the modern language of quantum theory, this is possible only if each and every quantum operation appearing in the instrument is proportional to the identity, which means that essentially the probability of outcomes that you get is factorized from anything which may regard the state, and actually it gives you no information about the state of the system, information about the system itself. So this in simple words is the summary of the no information without disturbance principle in quantum theory. However, there's another way of understanding the information without disturbance principle, which is based on a slightly different notion of disturbance, which is the one that you can see if you look at correlations with external systems. So if you have entanglement, entanglement is rather delicate. So if you perform a disturbing measurement, you typically destroy entanglement with possibly ancillary systems, So the essence of this information is actually very well summarized in this sentence that you can find in the book by Schumacher and Westmoreland. They essentially claim that quantum information is equivalent to entanglement. So in quantum theory, this is just, I would say, an equivalent way of rephrasing the notion of disturbance, actually non-disturbance. So non-disturbing the system, the system state, or disturbing or not disturbing entanglement correlations with external systems. However, if you go to a more general playground, it turns out that this is the real definition that you should check, that you should consider, because there are situations where you have measurements that leave the state unchanged. So if you look at what does the measurement locally, it seems that it does not disturb. However, you will find possibly an entangled state that is disturbed by your measurement. So despite this happens for every possible local input state. And I will give you an example, an easy example in a few slides, but first let me summarize the framework of operational probabilistic theories, which will be framework of theories that where we will discuss these notions. And they generalize concepts in classical and quantum theory, which are basically the notion of composing processes in parallel and in a sequence. So the primitive notions here are those of a system of the theory. For example, in quantum theory, systems are in correspondence with Hilbert spaces. In classical information theory, they would correspond to finite alphabets, for example. Then you have the other primitive notion, which is that of a test. A test as an input system and an output system. You can think of it, conceive it as a collection of possible events within a measurement, and the events are labeled by a finite set of outcomes. So the quantum prototype of a test is a quantum instrument, a collection of quantum operations labeled by some outcome label. So special kinds of preparations are special kind of tests are preparation tests, where the collection of transformations is actually a collection of possible states within the preparation process, and observation tests, which are in quantum theory they would be represented by P of n, so collection of effects. These kind of measurements where you just discard what happens to the system afterwards, you just let it outside the lab, or maybe you have a destructive measurement that annihilates your system. So it's, for some reason you disregard what happens after the measurement. The theory comes along with some rules, so that allow you to construct complicated experiment building on elementary processes like these boxes that I drew here. So you have tests, and you can compose systems in parallel. For example, this B, E, and G is a graphic representation of a tripartite system, a composite system made of 3 elementary systems. And then you have processes that can be run in a sequence. The condition in order to perform 2 tests in a sequence is that the output system of one test coincides with the input system of the following test. And then you can compose them in parallel. Composing 2 tests in parallel means that you have a composite system, like I don't know, 2 independent distinguishable particles, and you can run independently a test on one particle and a test on the other particle. So measurements on both of them. So you can construct complicated circuits with using these building blocks, and then in order to make the operational theory, up to now we discussed only the compositional structures of the theory, a probabilistic theory, we require that closed circuits, those that have a preparation test at the beginning and an observation test at the end, so where nothing is left either at the input or the output, are just joint probability distributions for the outcomes of the test. So, for example, in a circuit like this one, this circuit would be equivalent to a joint probability distribution for all the events appearing in the circuit. So this structure determines the fact that states live naturally in a real vector space, and the same for effects, they live in a real vector space. And you can think of events or as linear transformations in the space of states, transform the input state to the output state. An important primitive notion that we want to have in an operational probabilistic theory is that of coarse-graining. So you could define these without appealing to the linear structure that comes from probabilities, but it would be rather complicated. But the idea is very simple. So if you have a test and you have this joint partition of this space of outcomes, then you could also define within the theory another test which corresponds to disregarding some part of the information. So instead of asking what is exactly the outcome of the measurement, you just wonder in which of the sets to which of the sets of the partition it belongs. So you have this partition, you have indices, which is indexed by a label J. Every Yj is a subset of the set of possible outcome of the measurement, and two different subsets are disjoint. Their union is the full set of possible indices. And then there exists another test which represents a measurement where you only look for part of the initial information. And this discourse graining in operational probabilistic theory is represented by the sum of linear maps. So thanks to coarse graining, we can define the notion of an atomic event. So that the converse process of coarse graining is refinement. So if an event is obtained by coarse graining two events, then these two events are said to refine the event. So an atomic event is one that can be refined only trivially. So if the event is obtained by coarse graining some other events, then those ones, each of those ones, must be proportional to the original test. So you have no other choice. In the special case of states, in a causal theory, the atomic states are called pure. And as regards pure states, one important feature that some theories have, and in particular quantum theory has, is the existence of a purification. So if you have any state of any system, you can always regard it as a pure state, which is in which you prepare your system plus an ancillary one, and you just disregard the second system. So every state can be thought of as pure state where you lose some part of the information which is in the environment. And in quantum theory, also uniqueness of purification holds. So if you have two purifications of the same state, then they must be connected remotely by a reversible transformation. So the example of a theory where disturbance has to be judged on correlations and it's not sufficient to look locally is fermionic theory. So fermionic theory can be thought of as a variation of quantum theory, even though it has some deep differences. But the systems of fermionic quantum theory, are collections of local fermionic modes. So an integer number n of local fermionic modes, and every system of n modes is associated with the Hilbert space of n qubits. Okay, so n qubits, the space of n qubits is the same space that you use to represent the states of n local fermionic modes. And what you do is to choose a computational basis in every qubit space. You form a basis which is the tensor product of these bases. So you have strings of bits that label the computational basis, and pure states correspond to unit rays as in quantum theory, but with some care, some extra constraint. And the constraint is the following. So you have the Fock space, which is this Hilbert space, and can be separated into the direct sum of two subspaces, the even one and the odd one, which are the span respectively of strings of bits which have an even number of ones, and strings of bits that have an odd number of ones. And in fermionic theory, you have a parity superselection rule. So it's forbidden to form superpositions of vectors that have an even number of ones or an odd number of ones. So for example, for one local mode, you have the states 0 and 1, and then you might think of forming a superposition, but this is forbidden because you see 0 and 1 have different parities, and so this kind of state is forbidden, which means that one local fermionic mode is just a classical bit. You have two discriminable states and no superposition. But as it comes to two local modes, then you can form all the states of this kind, alpha 1, 0 plus beta 0, 1, and all the states of the form alpha 0, 0 plus beta 1, 1. And superposition of different parties, again, are forbidden. So essentially, you have two orthogonal subspaces, which are each one isomorphic to a qubit space. So 2 qubits in a direct sum, 2 qubits in a direct sum. So even though the local mode is a classical bit, the composition rule gives you also quantum superpositions in composite systems. And so the super selection rule tells you that if you represent states with density matrices, so instead of just considering pure states, you also consider mixed states. then the density matrices must be block diagonal. One block is the even sector and the other block is the odd sector. So this means that you can think of the state spaces of two subsystems in this way as block matrices. But if you compose the two systems, you don't have just the tensor product of the two state spaces, because the tensor product would correspond to 4 blocks, even, even, odd, odd, even, odd, odd, even. But in fermionic quantum theory, you are also allowed to do superpositions of even, even, and odd, odd. So you have these off-diagonal blocks, and the same for even, odd, and odd, even, because all the blue ones are anyway odd states, and all the red ones are anyway even states. So this means that the space of composite system is larger than the tensor product of states of local systems. And in technical terms, say that this theory does not satisfy what is called local discriminability, or also in the literature, you can find the notion of local tomography, which means operationally that you cannot, if you want to distinguish two bipartite states or multipartite states that are different, it might not be sufficient to do local measurements. This is different from quantum theory, where you can do tomography by local measurements. And mathematically speaking, you have this rule, which the composite system is larger than just a tensor product. It has some extra dimension. So let's see how you can violate the, how you can have a test that it does not disturb local states, but disturbs correlations. So think of a density matrix of a fermionic theory, which is block diagonal, even and odd block. And then you run a parity test. This is an allowed test in fermionic theory. You just measure the parity of your state. So one can easily prove that the parity test does nothing in the blocks, and so it leaves the states unchanged. So for example, if you take a mixed state of one fermionic mode, which is the mixture of the state 0 and state 1, if you read 0, then which happens with probability 1/2, then the state is 0, 0 after the measurement. If you read odd, then the state after measurement is 1, 1 with probability 1/2. And so the state after measurement coincides with the mixed state at the beginning. However, you can purify this state in fermionic theory, for example, with a pure state of this form. And if you apply locally the parity test on this purification, then you break entanglement. So this is an entangled state. But if you run the parity test in one of the local fermionic modes, you end up with a mixed state, which means that this test does not disturb the local state, but it disturbs if applied locally to bipartite states. So if you want to say that whether a test it disturbs, you really need to check its action not only on local states, but also on correlations. And so the usual notion of no disturbance is inadequate in the absence of local discriminability. We should raise the second definition that I showed you, the one where I quoted Schumacher and Westmoreland, to the status of the definition of what is a non-disturbing test. So non-disturbing test is a test such that if you take any ancillary system B and any state of your system plus system B, then you run the test, you just disregard the information that you get, but you're sure that in the end of the test, the input state is preserved. So now we know what is non-disturbance, and then by negation, disturbance in the general scenario of operational probabilistic theory. And now let's see what is information. What does it mean that the test gives you information about the system? So I just want to make a short remark that we are considering also theories where you don't have causality. Causality, mathematically speaking, means that there's a unique deterministic effect for every system of your theory, and this is equivalent to say that you can send information from the input to the output, but not backwards. You cannot choose some observation test and by your choice change the probability distributions at the input. So you cannot send information in this direction. But if you don't have causality, information can flow in both directions. And then a test can give you information both on the input preparation and on the output preparation. So if you have a test, the most general scenario where you can use it to gather information is some circuit like this one with a some preparation that involves an ancillary system, some measurement that involves the ancillary system. And the test can gather information both on the preparation phase and on the observation phase. So when does it provide information on the input state? Well, when you can make a measurement such that if you just coarse grain all the outcomes, so you will find a deterministic effect here, such that the probability distribution of the outcomes of your test will depend on the preparation stage. So changing psi, the probability distribution of your outcomes changes, and so collecting statistics of your outcomes, local outcomes of the test, then you have some information about what was the preparation of your system. And the same notion can be applied to gather information about the observation stage. So conversely, you don't have information, so a test gives you no information, or technically in jargon we call it no information test, if it does not provide information neither on the input, which means that for every deterministic effect that you apply here, what you get will be another deterministic effect multiplied by a probability distribution. So whatever is the preparation that you do here, you see that the probability distribution of the outcomes is factorized from anything that contains the state of the input, which means that the probability distribution of your outcomes gives you no information about the preparation stage, and also no information on the output, which is just the reverse condition. So for every deterministic state that you prepare here, after applying the test, you get another deterministic state multiplied by some probability distribution, which will be the distribution of your outcomes, which is then factorized from anything that regards the observation stage. So no information without disturbance, which is the property of quantum theory. In quantum theory, every test that gives you information must disturb the system, can be raised to a general property of theories. And so one can explore what are the theories that satisfy no information without disturbance. And in order to do that, we have to define the notion. So what does it mean that a theory has no information without disturbance? Well, it means that if a test is non-disturbing, then it gives you no information. In other words, if you want to test it, extract some information from the system, then it necessarily must disturb the system, which means either disturb the preparations, the state preparations, or disturb the observations, or both of them. So the theorem that we proved in the reference that I give you at the bottom of the page is that a theory has no information without disturbance if and only if the identity transformation is atomic for every system. And notice that this is proved under very general conditions, so that there's essentially no ingredient more than the framework of operational probabilistic theory. So we don't require causality, purification, local extremity, emanability, and anything like that. So this is the result. The identity must be atomic. So there's no way of refining the identity transformation apart from trivial refinements. There are other conditions for no information without disturbance. The first one is an equivalent condition, which is that every system has some reversible transformation, which is atomic. And the second condition is a sufficient condition, which is the existence of purification implies no information without disturbance. So it's sufficient to have purification, as in quantum theory, and you will have no information without disturbance. So also fermionic quantum theory, real quantum theory, which has variations of quantum theory that have anyway purification. These are all theories where you have no information without disturbance. So now what you might wonder, what if you don't have no information without disturbance? So what if the identity is not atomic? Well, if the identity is not atomic, then you can easily prove that it has essentially a unique decomposition into atomic transformations. And these atomic transformations satisfy this condition. So they are perfectly repeatable. So the outcomes that you can have if you do a measurement that is non-disturbing, so the identity, are outcomes that are perfectly repeatable. Once you see one of those, if you do a second measurement in a sequence, you will see the same outcome. So it's impossible to see different outcomes in a repetition of the measurement. So essentially, the kind of information that can be measured without disturbance is classical. So the information that can be measured without disturbance coincides with information that has classical features, like repeatability. You can think of it as some kind of objective, realistic piece of information that you can extract without disturbing the system. However, the structure that you have in general is that you have part of the information that can be extracted without disturbance and part that needs disturbance. So in order to gain again, to recover the classical systems, so systems where you can measure anything without disturbance, you have to formulate this stronger property, which is full information without disturbance. So negating no information without disturbance is not sufficient to have a fully classical theory. Fully classical theories are those that where full information without disturbance holds. And what is full information without disturbance is the property of those theories where every test can be thought of as a test that does not disturb, and where you can add some disturbance like a post-processing, just post-processing one. And you can prove that a theory is full information that has full information without disturbance, if and only if every system of the theory is classical, which means that there's a set of pure states which are perfectly distinguishable from each other. Then I would like to finish with this map.
Yeah, precisely. You're about.
Yeah. That's my final slide. So this is a kind of collection of the information that we have now about no information without disturbance, theories that satisfy it and theories that do not satisfy it, and do it in connection with other properties. So in particular, if you consider purification plus no information without disturbance, we have some examples which are fermionic quantum theory, real quantum theory, and quantum theory itself. Quantum theory is the only one among those ones that also satisfies local discriminability. Then you can have no information without disturbance even without purification. This is the case of PR boxes, the box word. You have classical theory that does not satisfy no information without disturbance. Actually, it has full information without disturbance. And then you have deterministic classical theory, where all probabilities are either 0 or 1. This theory has purification, does not have no information without disturbance, and has local discriminability. And then there's this other theory, which is very odd, which is outside all the sets that I drew here, and it's bilocal classical theory. So it's a kind of classical theory that features some non-locality, which pops up from the fact that you don't have local discriminability. So if you put two systems together, you have some extra degrees of freedom, some extra information that comes from the very composition of the system. So you don't have contextuality, because this is a classical theory. You can measure everything without disturbing. However, it's a strange theory. In order to make it consistent, the transformation must act in such a way that there must be some genuinely non-local degrees of freedom. And we conjecture that this theory, despite being classical, has no locally hidden variable model. So this is a curious question that we have in mind and we couldn't answer. It's an open problem in the literature. So thank you for your attention, and that's all I wanted to say. So now I'm ready for questions.